Hello, ladies and gentlemen. Welcome to our another lecture of data analytics in online form, courtesy of the long weekend. Generally, today we plan to finalize the numerical computation aspects of our subject. However, if someone can cover "Can you hear me? Are there no disruptions? Is everything okay?" Again, can you hear me? Could someone answer on chat? Okay, thank you very much. On Monday we have covered Markov chain Monte Carlo methods, and we've analyzed some simple examples, including a normal sampling from a normal distribution. However, that was a very simple case where nothing bad can happen. In particular, the curves of the geometry of the probabilistic space is okay. The curves of the probabilistic space is okay. These chains are getting stationary rather fast. They are wandering around the typical set very well. There are no significant problems. We've discussed some diagnostic aspects, but we saw that everything was okay for that case. However, this will not always be the case. Here we can see how the estimators of the means are going, of the expected values of each of variables are evolving. Here we can see how samples are located from the probabilistic space. Everything is nicely centered in the middle. Let's make something more complicated. Here we have something which is called a hierarchical model. We'll cover hierarchical models a bit later into the course. General idea is that our model is focused on modeling parameters theta I. Those parameters, however, are governed by normal distributions with certain mean and certain theta. So we do not have direct prior for theta I. Our prior for theta I is dependent on me and theta. And me and theta have their own prior. So there's a hierarchy of models where models of me and theta are given certain distribution. Moreover, the prior for log theta is rather wide because for theta is rather wide because we assume that we transform the we assume that that theta is not necessarily governed by its own distribution. It's we say that logarithm of theta has a normal distribution. That means generally that theta between that 97% of possible thetas are between exponent of -10 to exponent of +10. So this is a wide range of theta. Geometry of such plot is very complicated because geometry of such distribution is very complicated because when logarithm of theta becomes very small, then the standard deviation of theta also becomes very, very small. And the standard deviation of theta is very small, then it can move only so much in with respect to its mean value. So for negative values of logarithm theta, we have very little possibility of movement of theta. For large number of logarithm theta, we have a lot of possibility of movement. Here we can see how our samples are going over our distribution. And we can see the issue that's happening here. Initially, we get nicely to the area we can consider that might be a typical set. And we start to move here and we explore this part, but we do not get to this funnel here. This funnel is an issue. We can see on the contour plot, oh, it's very nice, something is focused here. However, we can see that our R hats are rather large, especially R hat for logarithm of tau is very large, because our estimators are not taking the proper values. They are not estimating the areas they should go to. No, they drift because we have a lot of we have complicated the geometry that tends towards biases in the estimation. The chains are getting stuck in certain areas, which focuses that there is no problem. Here are the areas of strong autocorrelation between samples, and this is very bad situation because we do not get the proper exploration of the space, and that is an issue that is unfortunately present in many cases in Markov chain Monte Carlo. Unfortunately, using classical vanilla Markov chain Monte Carlo methods, we have issue with finding that. We might see something on R hats, that's good, and small effective sample size, but that's not enough to cover everything that we really want. The help is always thanks to multiple chains. Having multiple chains, if even one of them is breaking, this is not a signal that, oh, randomly one chain got broke. No, it means that our model has issues, and those issues might be rather significant. That's why we need to evaluate our model, and we'll cover that later, how to diagnose model computation if such issue happens. Let's consider one more example, an example of a multimodal distribution, which is a mixture with half% probability of two normal distributions. One distribution is has a mean of 4/8. The second one has a mean of vector of -8, 4, and they have differently skewed covariance matrices. And we can see how the plot of this figure works. Here is the point 0, 0. Here is the one that's in negatives, one is in positives. So we have two areas of high probability because this is a mixture, two modes between which the samples can come from. And when we sample this distribution, we not necessarily get so bad ideas, because as we can see from sampling, we get values that are located in one of the modes, and split R hat is very nice, as it can be seen in the plots. However, knowing this, we have a problem because we get stuck in one mode of the distribution. So it was not possible to diagnose that using values of R hat. We just got stuck in it, and we really couldn't do much more. If we increase the number of samples, then we can get much bigger problems, because increasing the number of samples for longer periods, if we do 200,000 samples, we will get some values with huge R hats and abysmally small expected sample size. Chains look okay, but chains show us that we have switched between two modes. You see, here we start in one mode and then we switch to another. So we have something like this. We start here, we move here, and we start moving between the, we don't do not move between the mode, we just have a situation that one sample from here just gets dragged into this one. And this is a very difficult case for vanilla Monte Carlo to approximate. So, as we can see, Markov chain Monte Carlo is a method that allows us to compute stuff that we need regarding distributions of expected values. It can help us generating values from the it can help us generate values coming from the values that are coming from given distribution. We have Metropolis-Hastings algorithm that shows us what is necessary. However, it can still have issues when covering the distributions of when covering more complicated distributions. It can get stuck. It can get stuck between modes. It's not the only possible solutions that we can really use. So, what we can do? Well, we can work on that by improving the by improving our methodology. We focused on the very simple, very classical Metropolis-Hastings algorithm. This is, however, not the only one method that we can cover. And the method that we are actually want to use is the method of Hamiltonian Monte Carlo, which is a method that is currently state of the art of the Markov chain Monte Carlo methods. Hamiltonian Monte Carlo is a methodology that is implemented in STAN, in PyMC, and in multiple different frameworks, and its idea is to generate more efficiently distributed samples over the typical set, thanks to the following of the curvature of the typical set. But if someone was in some kind of way following what I was saying for the last few lectures, they should observe that we don't know the typical set. Typical set is unknown to us. So what actually we can do? Well, while the typical set is not known to us, we still have formulas for probability distributions. And we can use derivative informations to move around that curvature, because curvature of the any function can be determined by following its derivatives. Moreover, equation of movement are actually something that can be followed using certain differential equations. And the idea of Hamiltonian Monte Carlo follows for the concept of how would a point slide over the hypersurface of probability distribution in this very, very large space. Well, it would start to move not on the, when we have two-dimensional, it would not move on the flat surface, but it would move over the mountain of probability distribution in small dimensional cases. In higher dimensional cases, you have to believe me. But in order to get that movement of points sliding over the surface, we have an issue that for that movement, the position in the space where the space won't be enough. We would need to know, in order to govern the equations of movement, you should remember from the second law of the dynamics, we need derivative, that is speed and speed and position, or position and the momentum of the certain point. So, how to get differential equations of a point moving on the surface of the probability distribution function? Well, this is actually possible thanks to so-called Hamiltonian mechanical formalism. Hamiltonian mechanics is one of the way of describing the equations of motion of objects. If you remember something from control theory, on some classroom there was considered a Euler-Lagrange method of constructing differential equations describing the physical system. This was Euler-Lagrange and Newton-Lagrange are two possible methods of construction that systems. Euler-Lagrange methods focuses on certain function called Lagrangian, and its generalized energy functions, which generally comes from the idea called variational calculus, where you kind of find the optimal representation of that movement, and that movement are the proper differential equations. Different approach is so-called Hamiltonian dynamics, which uses a function that is very close to Lagrangian, which is called a Hamiltonian. Hamiltonian function is a function that you've already probably met in the optimal control derivation when considering Pontryagin maximum principle. However, in this case, and in general case where Hamiltonian comes from, it comes from the representation of movement of object or general dynamics of object as a connection of generalized position and generalized momentum variables. And in case of Hamiltonian Monte Carlo, we create some certain dummy variables that are supplementing movement of our system by representing its momentum. Hamiltonian is defined as in our case as a negative logarithm of the posterior distribution, and because we are not really interested in posterior but something that's proportional to it, just the joint probability, that is product of a likelihood and a prior. Excuse me for a second, I have to talk with my dog to be silent a bit. Sorry, I had to talk to my dog. Show yourself! There's a dog, and it's a very loud dog, which can be very loud. So, regarding our Hamiltonian formalism, we defined it as a negative logarithm of the joint probability density function, which is a numerator of it's generally a numerator of the posterior, which, as we said before multiple times, is enough to sample from the distribution. We can then observe that because of the structure of joint as a product of likelihood and prior, we can, and this is a logarithm, we can easily split it into two parts. That is the logarithm of likelihood and the logarithm of the prior. So, we have two functions, kinetic energy and potential energy, that are described in our Hamiltonian. And the idea of the Hamiltonian equations is that we can compute the Hamiltonian equations by differentiating our probability, our Hamiltonian with respect to for the equations of motion of position by those momentum variables, and for the equation of momentum by the position variables. Here you can see this is with plus and this is with minus sign, and you can associate it with adjoint equations from Pointillion principle in optimal control theory, and that actually makes very much sense because these are approximately the same equations. The adjoint variables of Hamiltonian from optimal control theory are generally certain kinds of generalized momentum representation. So those equations come from the choice of the kinetic energy, which is related to our likelihood. So the idea of our model is that we sample momentum from given point in order to we start with certain point in probability space. We sample momentum using the probability distribution. So we have a pair of 2 points. The position, which is probability variables that we want, and momentum, the dummy variable. This gives us an initial condition for differential equations that are allow us to move to a new point in the probability space. This is good because we move around the curvature of the typical set this way. Then we are not interested in the momentum because it's a dummy variable, we drop it. So we perform marginalization of this more complicated distribution and we move to the just again to our variables. Problems that are come here to make it work. First of all, the kinetic energy of the equation, then where those differential equations come from and how to solve them, and finally how to avoid spinning around the typical set and returning to the same point. So generally idea is that we can use this kinetic energy equations in order to use some certain normal momentum distribution to move to sample from P conditional on Q using certain normal distribution. And matrix of that distribution is computed using the during the warm-up of the algorithm. So during sampling, when we still will drop those 1000 samples, for example, we can use the information that come from to better tune the matrix M. Then we have the problem of differential equations. One would think that computing those differential equations from this complicated formulation here might be difficult because it is it requires us computing multiple partial derivatives. Q is our high-dimensional vector we had an issue with. It's hard for computation. P is the same dimension of variables that make no sense. So what can we do with that? Well, fortunately, there is something called automatic differentiation. Something that was developed practically thanks to deep learning revolution. There were multiple frameworks for automatic differentiation that transform that when you put equations, for example in Stan, as using symbols, those symbols are converted then to a certain graph. This graph is then differentiated using the chain rule of differentiation in order to obtain those partial derivatives, and the code that is for our computation is constructed during the compilation, for example, of a Stan model. Analogous approaches are worked in also in different frameworks. Just a quick reminder. Automatic differentiation is not the same as symbolic differentiation. We do not go over the symbols, what is the derivative of given function, etc. In automatic differentiation, every mathematical operation can be reduced to, in computer, can be reduced to a sequence of more or less complicated numerical operations, multiplications, additions, etc. Those things are easily differentiable. However, we are not differentiating the functions that compute given values using them, but we use we differentiate the code representations of those functions, which often can be some kind of an approximation. For example, a sine function in computer is obviously an approximation. It's not a real, not some real sine, because we cannot compute real sine that easily. So, having that, we get those differential equations, we get the code. But then, how to solve those differential equations? We have an issue with those equations because those are the equations of undampened motion in a very high dimensional space. The problem with simulating such systems is their chaotic nature, and is the issue that it is a natural tendency of differential integrators to numerical integrators to introduce certain artificial dampening to the system. It comes from the case that when you are modeling the when you want to construct a solver, you want it to preserve stability. And unfortunately, undampened oscillations or non-vanishing, non-dampened movement, which we want to move around the probability space, is unfortunately something that is often converted to a dampened move. So it would, in normal differential equation methods, introduce biases during such computation. However, there is a special class of methods called symplectic integrators. Symplectic integrators have this nice property that they preserve the Hamiltonian function during integration, so they can be used to simulate undampened oscillations over a very long period of time. They will just introduce periodicity. And one very special case of symplectic integrator is a very simple one called a leapfrog integrator. A leapfrog integrator is a very simple first order method for solving differential equations with fixed step, which fortunately we can take to be small, that has this symplectic property, and in contradiction to all other symplectic integrators, this one can be implemented as an explicit one. So it does not require from us solving systems of high order algebraic equations to determine its next step. This is the classical problems of inverse Runge-Kutta methods. And in case of leapfrog integrator, its structure is convenient enough that for systems in the form that we are considering here, we have no issue with solving them explicitly. And that is a very, very good situation. Additionally, to improve the stability of movement, we solve those equations not only forward but also backward in time. This again, in normal cases, is a problem, because when you are solving stable differential equations backwards, they become unstable, because generally after all the dust settles, differential equation solved backwards is just solving the negative of the differential equation with a negative right hand side. So everything that was stable becomes unstable. Here, however, this is not that big of a problem, because our equations are naturally energy preserving, undampened, so they are oscillating, not unstable and not asymptotically stable, so reversing time won't be an issue. So the idea is that instead of just following from this one point, we determine the sequence of points for solving both upfront and back, and then we use a variant of Metropolis Hastings condition in order to accept the step. So this is a very complicated method of generating some kind of proposal values. However, it still follows our distributions, generates our Markov chain, and is much more numerically efficient. Final aspect that we want is something called no U-turn sampling, also called NUTS. The idea of no U-turn sample for Hamilton and Monte Carlo is that we are afraid of situation like this, that we start from this point and move to a point that actually, using this entire oscillation aspect, would be closer to our initial step that the road that we followed. So the idea of no U-turn sample is to choose point that's only that move without turning back in our distribution. And there are certain conditions that verify that. So so in Stan and other we are using variants of no U-turn sampling. And this has multiple benefits, but one of the main benefits of what we really want to introduce in our model is that we have the nice advantage of that construction of our movement equations introduces our as the additional self-diagnostic tools. What I mean by that? I mean that for those equations, when we encounter complicated geometry, then our model will start to have problems with solving differential equations with a fixed step. Because if you remember something from numerical computation, whenever we introduce the problems of high curvature or significant issues in computation, then we have the problem that our variables that our differential equations tends to destabilize. This is the case as we covered in numerical methods. Before that, system kind of loses stability because for example, when we have a very sharp drops in the time derivative, then our system becomes naturally unstable. And it causes that we get values that tend to infinity very, very fast. Such numerical disturbances are called divergences. Those divergences cause the situation that our system has encountered the problem of solving differential equations and rejects our proposal, our next step from computation, and will try again. Its solution of differential equation found by those initial conditions has diverged, has destabilized. So this, instead of following the typical set, it just drops here. And this actually is not a bad thing. It's a good thing. It's a good thing because it provides us with certain diagnostic possibilities of finding the proper values of finding the problem in our curvature. It can be used to distinguish the problems where the posterior behaves weirdly. And this is something that we want, because if we ignore those situations, all our estimations will be biased, our computation will be generally wrong. And as we've seen previously, it's not always detectable using R hat, for example. So, finding such situations allows us to do some modification. Okay, and just to cover some additional examples, we can look at Hamiltonian Monte Carlo, how Hamiltonian Monte Carlo works in Stan. So I have a bit of code that uses the uses the Stan code for those examples that we've used before, and okay, I'm not finding this code at the moment, so like not much issue. Generally, we sampled from the normal distribution. We have chains computed here, and with saving the warm-up, we can compute how everything happens here. So as you can see, the samples getting here, we get again estimates very nice for the variables that we had before. We have nice movement of points around our typical set. The case of normal distribution with unit variance leads us to a very nice, very consistent problem. In case of more complicated system, however, with a funnel, we will have a bit more issues. As I've shown you before, that hierarchical model can be a bit problematic. And sampling of this distribution here shows us that getting samples from the entire set might be a bit complicated. So starting with our warm-up that we have here, we are following this idea, and we then move to the proper spaces. And here on the red are marked points that were dropped because they had divergence. So we can observe on such pair plot what happens when we have those divergences. And detecting those divergences allows us to fix certain issues, because our original Stan code here was very simple. We had priors for mi and log tau, and we had the proper values of tau here. But this is so-called centered parametrization of hierarchical models. It is famously known to create issues, especially in cases when we do not have enough supporting data to remove us from the problematic cases. Because using proper data, we can handle some of those things. On other cases, if we have improper data, we will have more cases. So this is not an obvious situation that we always need to drop the centered parameterization. However, if we take a non-centered parameterization, we can actually do something a bit different. That is, instead of modeling this theta as a normal distribution with a mean mu and standard deviation of exponent of logarithm of tau, we can get again those two parameters, mu and log tau, and we can create a new auxiliary variable eta, which is no unit normal distribution. However, we can convert it using mathematical formulation from normal 0, 1 into normal with mean mu by adding mu and multiplying it by standard deviation exponent of log tau. So using this very simple structure, we have significantly modified our computation, despite the fact that we preserved our computational character. These two formulas are numerically analytically equivalent. However, for Hamiltonian Monte Carlo, when we use this second model, we get much better behavior. As you can see, computing eta has absurdly high number of the effective samples. Every variable has an R hat of 1. Converted theta also have R hat of 1. And in previous case, we had some problems with R hats, right? And when we consider the sampling here, we get the samples that are exploring a funnel a bit, and now they have no issues with divergences. So the the sampling is much improved. And what we can see, the traces of plots are also much better. And this is something I don't remember what was. So as you can see, we have found divergences in the model, and we've modified the model, preserving its structure, to behave much better than previously. Unfortunately, this is not a panacea for everything. We cannot use non-centered parameterization for everything, because in certain cases it will break. This is a situation that in certain models without data, with little data, the problem can be solved by non-centered parameterization. But in certain models, we have enough data that moving into non-centered parameterization would actually introduce problems which wouldn't be present without that. So this is something that requires careful diagnostics, what's happening, and we will be covering that in the scope of lectures considering Bayesian workflow. Future plans for our lectures are causal inference, posterior likelihood functions, prior selection. Then we will move to Bayesian workflow, model comparison, and the hierarchical and multi-level models. So those are the plans for following lectures, for which one we have planned already for the 2nd of May. So that will be let's say nice excursion into the long weekend. Then the issue is that in my calendar May looks really dire, and I will be reaching to your starosta of the groups to get some kind of info, because on Friday I am in delegation, so there will be no lecture, that's it. And we can consider doing it on Monday if there will be will for that. I don't have will for that, but I will manage. So if there will be interest, there will be a lecture for 9th. The lecture will be on Monday of the 5th. Then on 16th there's no lecture because there are juvenalia. So I understand that this is covered by a rector, so we won't be doing that. Then on the 23rd of May I'm on a conference, so again we would have to consider perhaps 19th. And on the 30th of May I am here, so there won't be an issue with that. So be aware that there will be still multiple online lectures. I'm not sure that will be on the 5th, but we will see how it's going on regarding that. And because it's a long weekend starting, so we will do a shorter version lecture today, and we will resume our normal lectures for the later part. And also, like I don't want to start a new topic. I said I had it about computation now, so starting a new topic would, I think, be counterproductive here. Everyone wants to move to the grill, and on the second, maybe we'll want to have a little break from grilling and stuff like that. So, okay, thank you very much. Have a nice day. Unless there are any questions, I can wait for questions for a second. And if not, no questions, then we are finishing for today. Okay, thank you very much.